So something called Newton's method is a way to approximate x-intercepts of a function. And you can look at x-intercepts in many different contexts. It could actually also help you solve equations or find roots of equations. So what is Newton's method? Well, Newton's method uses linear approximations in sequence to approximate x-intercepts. So that's what we're going to look at. This video is more, not really an example, but to lead you through the process to understand Newton's method. Okay, so I'm going to switch to a different program called GeoGebra, where I've built an example of how Newton's method. Okay, so over here we have GeoGebra, and over here I'm going to be writing notes for you. What you see here is the function f of x equals the natural log of x. That's the curve that I've graphed here. And you can clearly see so I chose a very simple function that has a nice x-intercept of 1, 0. What we're going to do is pretend that we don't know that's the x-intercept, and our goal is to approximate the x-intercept, okay? And that's through linear approximations. So the first thing we need to do is guess an x-intercept. Guess an x-intercept, an x value. So what we'll do in this case is, let's say we guess that x equals 2 might be the x-intercept. And a lot of this is built on that maybe this function is really complex and we don't even know exactly what the graph looks like. So we wouldn't be working with a graph to actually do this process. I'm using the graph to show you how it works. Okay, but let's say we choose x equals 2 to be an approximate. And then what we're going to do is, once we guess the x-intercept, we're going to find the point on the graph, the point on the function, with that x. Okay? So now we've got our point on the function, and now we're going to look at the linear approximation. So create a linear approximation. In other words, the tangent line. So I'm going to look at the tangent line at this point. And so now I have an approximation for the function at where x is 2. And what that does is it gives me another guess. I started with a guess of 2 to be the x-intercept. Now my linear approximation is going to give me this x value here as an approximate x-intercept. So now we start the process over. We guess a new x-intercept, which would be this point right here, the x-intercept of the tangent line. So now we have this x-intercept. Then we're going to use that to get another point on the graph down here for that x. And we've got another point on the graph now, and we'll look at its tangent line. But let me zoom in here a bit so we can see what's going on. So we started with this approximate x-intercept, got the tangent line to the function at that point, got a new approximate x-intercept from this line, which is easy to calculate. Then we look at this point, and now we're going to look at its tangent line, which looks like this. And now that tangent line gives us a new approximate x-intercept right here. So we have this approximate x-intercept. And you can see every time we're doing this, we're getting closer to the actual x-intercept of 1, right? And if we continue this process, we'll get another point right here. Once I have that point, then let's zoom in further. Here's the actual x-intercept. Now I want the tangent line at this point. And now you can see this tangent line at this point is a line that's very close to the curve. And if I zoom in further, the new approximate x-intercept is right here. You can see it's bigger than 0.98, very close to 1. We can actually calculate. And you can keep going as far as you want until you get as close as you want. But the point is, you can keep creating these linear approximations. So the idea is create linear approximations, use the line x-intercept as your approximate function x-intercept. If that's not close enough, then use this new x-intercept, use the line x-intercept to get a point on the function, calculate the new linear approximation, and repeat. And you can do this as many times as you like. Now you've got to be really careful though. If we come back over here to this function, remember we started with an approximate x value of 2. That was totally random. So let's zoom out here. So here's the function. Let's say we choose an x value of 3 instead of 2, just for whatever reason. Then we'd want the point on the graph that corresponds to that x value of 3. That point would be up here. We would use the linear approximation or the tangent line to get a new approximate x-intercept. So now we have the tangent line. We get this approximate x-intercept over here. And yes, that x-intercept is closer to 1 than 3 was. However, the next step in this process that we repeat is to find the point that's on the curve whenever x is right here. Well, the function natural log of x is only defined to the right of the y-axis. So this now, Newton's method is going to break down, and we won't even be able to get a y value on the function. So 3 is a bad first choice. So how do you decide an x value to start with? Well, you could use some calculator techniques to plug in values. So right here, if we want to find the x-intercepts here, we would like for the y to be 0. X-intercepts are where y is 0. We would, sorry, I shouldn't write 2. We would try to find, using a calculator maybe, things that we could plug in for x that seem to be small, seem to be close to 0. When we find one that seems suitable, maybe choose that to be the starting point for x. Now again, this function is very simple, so it's not difficult at all to do that. You could even find the x-intercept directly to be the ordered pair of 1, 0. But if you have a complex function here, it's much more difficult, and so you may want to use a calculator to get some guess as to a good x value to start with, and then start applying Newton's method and iterate it until you get as close to the x-intercept as you like.